Have you ever wondered how we can build powerful quantum computers when individual quantum particles are so incredibly fragile? The Quantum Threshold Theorem provides a theoretical foundation showing that reliable quantum computation is possible even with imperfect quantum components. It essentially states that if the error rate of individual quantum operations is below a certain critical threshold, then quantum error correction can suppress errors exponentially, allowing for arbitrarily long computations. The core idea behind this theorem is the power of quantum error correction codes, often referred to as QEC codes. Unlike classical bits that are either 0 or 1, qubits can exist in a superposition of both states. This means a single bit flip error in a classical system is simple, but errors in quantum systems can be much more complex, affecting superposition and entanglement. QEC codes encode quantum information redundantly across multiple physical qubits. This redundancy allows us to detect and correct errors without directly measuring the fragile quantum state, which would destroy it. To put this into practice, imagine you are performing a quantum operation. If the probability of an error occurring during this operation is below the threshold, typically a very small fraction of a percent, then by using more physical qubits to encode one logical qubit, you can reduce the effective error rate for that logical qubit. This process can be iterated, meaning you can encode encoded qubits, creating layers of protection. This recursive encoding drives the error probability down, for below what is possible with single, uncorrected qubits. A key concept here is the error syndrome. Instead of directly probing the logical qubit, quantum error correction measures a syndrome, which is a pattern of errors, to identify where and what kind of error occurred. This measurement itself must also be sufficiently accurate, which is part of the challenge the threshold theorem addresses. One popular approach for building these fault-tolerant systems is using topological codes, like the surface code, which are inherently robust against local noise and naturally fit into this hierarchical error correction strategy. So, the quantum threshold theorem does not eliminate errors, but rather offers a powerful assurance. It tells us that as long as our physical hardware can perform operations with a certain minimum level of precision, we possess the theoretical tools to scale up to large, fault-tolerant quantum computers. This theorem is a guiding light, providing a clear pathway from noisy intermediate-scale quantum devices to the truly robust quantum computers of the future, by managing and mitigating the inevitable errors inherent in quantum systems.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.